Hello. This video is going to be about auto-tuning a second order plus dead time system using gradient descent. But what I want to start out with is what I had done on a previous video where I had used the least squared method, the second order plus dead time least squares. And what I have is the same uh, text file with the control output. This is a control output. This was the cyan line is the actual temperatures response, and then what I'm trying to do is find the parameters that will provide a differential equation that will simulate the actual response. And when I have the real parameters, I can calculate out the controller gains down here. Again, you should see the previous video about the details on using the least squared system. Now, what I want to get into is the reality of using gradient descent, and it's not good. And what happens is that so many instructors will show you a nice, neat cone, maybe x squared plus y squared, and you're supposed to find the minimum. You start out, like, say, at point x equals 1, y equals 1, and then what happens is you're supposed to follow a path down to where you get to 0, comma 0, and the algorithms are going to work. I mean, there's no noise. It's not real data. And that's what I have problems with all the instructors. Plus, they never, never, ever show the calculations, or they rarely show the formulas, um, real working formulas. So again, let's start out with the gradient descent here, and let's see, that's the Nelder-Mead. This is the gradient descent. Okay, now let me explain what I'm doing with the gradient descent because this is super simple. Uh, Most of this is the same. I don't need to have import a library. I'm writing all this from scratch. So I'm not using the SciPy ODE-int or anything like that. Or no, I need the ODE-int to do the simulation in the cubic splines, but I'm not using the least squares or the minimize routines. I got the same print routine, the same calculate PID routine, the same init parameters. Um, this should be a 0 to be the same. I have a bounds array, and one of the problems with using a 0 in this case is that my bounds happen to be 0. In other words, the dead time should never go negative. It should always be a top positive time because the dead time um, is always assumed to be, well, it needs to be positive. You can see right here that because it's positive, it subtracts from the time to simulate the delay. So this is the same differential equation that I had with the least squares of the Nelder-Mead. And then this calculates out the second derivative, and it gets integrated. So this is the rate of change in the temperature, and this is the second derivative of the rate of change in the temperature. This is uh, the same also, except for I just return the difference, or I'm returning a mean squared error instead of a difference in the least squares. And then this is where I have a significant difference from the other routines. I'm calculating the gradient or the difference of del f. So I have my function, which is this function up here. I was trying to write this in a general way, and these are the parameters. So what I need to do is I start out with my derivative of my parameters or my gradient, and I save it away. And for each one of the dimensions, length p, I take a small step positive and a small step negative, and I subtract the two results, and I divide by 2 times h, which happens to be my little increment for taking steps. And then I return dp, which is actually the gradient, the derivative of the parameters. This is my gradient descent program, but the rest of this is pretty much the same as the Levenberg-Marquardt or the least squares or Nelder-Mead. So the gradient descent um, is figuring out the gradient, and I calculate the gradient norm, and I'm not really using it in this simpler version. And what I do is I uh, calculate out a step, and the step is subtracted from the alpha minus the gradient, or it's equal to the this alpha, which is the learning rate, times the gradient, and then I add that to the parameters. So this is actually an array of 5 uh, steps that's added to the 5 parameters. And this is my bounds check to make sure that I don't go out of bounds. And the only parameter that goes out of bounds is the dead time. Then I calculate out a mean squared error, and I'm printing out the information here, and I'm printing out the norm, and I can print out the parameters, but normally I like to print out, see how the the steps or the parameters change. And what I'm going to do is I'm going to, well, I don't think it makes any difference because I'm not going to run this one anyway. And the reason why is that it takes forever. In fact, it doesn't even get to a solution usually. And the reason why is because if the points are too if the learning rate is too big, it ends up bouncing off each one of the parameters. It goes plus and minus, plus and minus, plus and minus for each parameter because there's no direct route. It's almost like there's a twisted valley, but you got to remember this is 5 parameters, so it's a 5th dimensional um, terrain, and you can't go in any one direction without making one of the parameters uh, cause the mean squared error to go up very, very high. And the other problem with this is that whenever you take a small step, and this is my step up here, uh, e2 2 to the minus 7th. This is my small, or this is my learning rate. This is my step size. This is for figuring out the derivative. This is for the learning rate and figuring out how far I'm actually stepping. Um, what happens is that every time I take a small step, if I make the step too small, it's just going to figure out a new direction, and the new direction is not going to be, uh, it's going to go in a new minimum direction, but it's going to run into a wall, but it's always going to be trying to find the minimum uh, value for the next step, but that's not always the best solution. And you'll oftentimes see the instructors talk about a momentum system. And I've tried that. I don't like it because what happens is that again, it kind of bounces into the walls. But I can tell you what really works. What really works is a line search. So let me come here, and this is exactly the same, except for right here, I have calculated the mean squared error, and then if the mean squared error is less, then I calculate a new mean squared error, and if it's less than the previous one, I keep on searching in the same direction. Now, that doesn't mean it's going to be lower than if I had taken a step and reevaluated the mean squared error. It means that I'm just going in some direction. It might not be the minimum if I got to the next point, but it doesn't interfere. So in other words, it will find maybe uh, 20, 30 steps in one direction. And what happens is that this will actually get a solution much faster than using the gradient descent without the line search or with the momentum. So I'm going to just run this. It's going to take about 2 minutes. Now, whenever you see it pause, what it's doing is it's actually in this loop where I'm not printing it out, but it's doing a line search. And you will see that the mean squared error drops pretty quickly here, but this is taking a lot longer than either the least squared or the Nelder mean. So the question is, why bother with the gradient descent? At least it doesn't work very well with real data or with trying to minimize uh, the, the model for tuning parameters. So come on, it'll come back soon. Anyway, it's kind of caught in this loop right here. It will come back in a moment. This is not my fastest computer. I should cut this out. There it goes. So it's taking some pretty big steps. Now notice also that it's taking some steps in the wrong direction here, but it's going to start dropping down fairly quickly. And this will take, I'm not going to wait, it'll take about 70 seconds to get to the minimum, but the minimum is that I'm searching for is only zero point 0.3, not 0.1899 like I did with the Nelder Mead or the least squares. Now you see here the line search went down very, very quickly, and we should get to an answer here pretty quickly. Well, I'm not going to wait. So another thing that you learn about with the from the instructors is that there's a method called adaptive gradient, and let me just show you what that is doing. That's the gradient descent. Okay, that's the line search. Okay, this is the adaptive gradient. Now, what the instructors don't tell you is that yeah, it's a nice idea, but it doesn't always work. And let's just go through and show you what the adaptive gradient does. After we have the gradient, I have the norm again. Okay, again, that's just for me to print out information. But what you have is a sum of squared errors, and what you're doing is you're taking the gradient and you're multiplying it by itself. So I'm using the dot product. Now, what the instructors don't tell you is that you need to have some sort of factor up in front of this, because if you don't have this multiplied by some small number, the sum of errors squared gets to be huge, and that affects the step size later. So I have alpha times the gradient, and then what they do is they divide by the square root of the sum of squared errors, or sum of squared errors, and then they have this little epsilon here to keep from dividing by 0. But the problem is that this number gets to be so big so quickly that the step size gets to be too small, and it takes forever to get anywhere. So again, this doesn't work if you don't have this extra factor in here. What this does is it slows down the rate that this divisor here increases. And again, without this number, it doesn't work. Another thing is that if you need to use the line search, and the reason why the line search is necessary is because after you calculate the gradient here, I'm not calculating the gradient again. So while I'm doing the line search, I'm not adding to this sum of squared error, and it's reducing the mean squared error. Now in this case, it should get the answer in instead of 70 seconds, it will be, let's see, 50 seconds. So again, this is a little bit faster. So let's run this so you can see what's happening. Now, at this point, I'm actually plotting the difference, how much each variable is changing. And you can see that because that SSE is small, the steps are very big to begin with. But due to the line search, it decreases fairly quickly. Every once in a while, it takes a jump in the wrong direction. And what we're looking for is 0.3. And when it gets to 0.3, it'll stop again. If I try to make it go, wait till it gets to 0.25, which again is bigger than 0.1889 or 0.1899, like we had with the least squares or Nelder Mead, it will take an hour. So the point that I'm trying to make is that the gradient descent is not very efficient. Uh, what makes the Nelder Mead efficient is the fact that it's using Hessians to figure out the the acceleration rate, and it can use that to figure out a quadratic equation, and you can figure out the minimum, and it can avoid taking all these small little steps. Let's just wait for it to come up with the minimum here just so you can see. And you can also see that what's happening here is that a lot of these parameters are going minus, plus, minus, plus, minus, plus, and that's because the terrain is very, very rough. And again, each one of these things is kind of like a dimension, and you're bouncing off the valley walls in 5 dimensions. So what you're seeing with the instructors is they got this nice smooth cone shape, x squared plus y squared, and that's not reality. It's not reality, and someone should pin them down on that. I would be the student from hell, because I would. Now you can see that the mean squared error, or the norm, is getting smaller and smaller. Oops, almost there. There we go. Well, this took a little bit over 2 minutes on this. This must be because this is on a slower machine. But anyway, you can see that it gets a very decent answer. And so if you're going to use the adaptive gradient, which I recommend, I also recommend that you have a scaling factor that the instructors don't tell you about. I also recommend that you use the line search so that you can search uh, in a constant direction without calculating out a new direction at each step. So that's the point that I want to make. Hope you enjoyed the video and find it instructive, and you've got a small dose of reality on a real system. Bye.